is the most common was nitrogen. I think Glenn maybe went over a little bit of this. The nitrogen tends to make the diamonds yellow. It can aggregate. There's various forms of nitrogen in these diamonds. But those diamonds are type 1 diamonds. The other one is type 2 diamonds, and more specifically what we're looking for here at Park is type 2A diamonds, and that's where there's no detectable nitrogen, no detectable boron. And so the interesting thing here is that there tends to be a high proportion of these type 2A diamonds compared to any other deposit in the world. And we think these diamonds come very deep in the earth, maybe around 660 kilometers, so close to the lower mantle, upper mantle boundary.
Okay.
And they tend to have very specific inclusions. They probably grew slightly differently. They look slightly different. They tend to be elongate, resorbed, kind of frosty. And they also have very unique inclusions. So what we've got here is two FTIR spectrometers, so 4A transformed infrared spectrometers. Y'all are geologists. Any experience with spectroscopy? Sort of. You understand the concept, right?
Yeah.
So it's using infrared light to kind of bounce into the stone, and what happens is that the diamonds, one thing we do with this is the park actually has one of these spectrometers that we own them. One really nice thing with these spectrometers is that they can identify diamond very easily. So people find stones and they take a diamond in the park, and bring it in and test it on the FTIR spectrometer. They're not sure right at the stone. There's very unique vibrational patterns. So an FTIR spectrometer is very good at picking up vibrational patterns in these stones. The diamond has a very unique set of vibrational modes that will help you to easily identify the stone. It's got a unique pattern you can tell away from any other kind of material. The other thing that is the nitrogen in these diamonds also has unique vibrational patterns, and so we can identify whether the stone has nitrogen or not. So there's this specific region we look for. If it's a flat line, it's a type 2A diamond because there's nothing in here that's vibrating those frequencies. It's got a bunch of peaks. It's probably a type 1 pattern. And so we can tell with these FTIR spectrometers. We've also got a microscope. So we're also, in addition to, part of what we're trying to do is figure out statistics on the type 2A diamonds here. But the bigger picture is we want to look for inclusions in these stones, and that'll help us understand how the diamonds get formed. So we think they're probably not like, one of our colleagues at GIA has done a lot of work on the inclusions in type 2A diamonds from around the world. And the tricky thing is type 2A diamonds usually are very, they don't have very many inclusions. But he's done some work showing that these diamonds did form deep in the earth, around 660 kilometers. And so what we're trying to do is find more diamonds from Arkansas, and hopefully they'll have similar inclusions that'll kind of tell more of a geological story of where the lamproite here came from, what it may have sampled on its way up to the surface, and why this kind of deposit is different from your more typical kimberlite type deposits around the world that don't produce a high percentage of 2A diamonds.
Okay. Thank you very much.
Yeah.
Appreciate that.
Mike, is that?
I only got the last half of it, but no, I think, yeah, I mean, that's the goal. There's something unusual here in terms of the distribution, and we're trying to figure out why. I mean, it's kind of cool for the park because it's exciting and different, and then at the same time trying to establish that some of these diamonds do appear to have come from 600 kilometers down in the earth.
Yeah. Have you all studied the deposits down? I'm sure you've studied the diamonds from the deposits down in Australia, which are also from a lamproite rather than from kimberlite.
Yeah, I mean, Argyle being the most famous.
Yeah.
Argyle's unique.
They have a much higher percentage down there of pink diamonds than any other place in the world that I know of. The original landholder of this property, Howard Lars, who was the son of Austin Lars, who bought it from Huddleston, John Huddleston. Howard Lars had a pink diamond, uncut, he wore in a ring. I always wondered, I know that passed down through the family, but where is that stone now?
Yeah, I've never heard of any pink diamonds coming
Yeah,
from here.
one pink diamond. He bought it, was found by a tourist, and he bought it from them so that because he knew it was so unusual that he wanted to keep it so he could show everybody.
That's cool. Yeah, I mean, pink color it's not well understood. We know what feature causes pink color, but it's not well understood exactly what it is in the atomic structure of the diamond. But it is related to the same thing that causes brown color. And so Argyle's also famous for its brown diamonds.
Right.
The terms champagne,
Yeah,
cognac, and
that's-
chocolate,
That
that's
was
all
a
came.
marketing ploy,
Yes.
it's called it a champagne diamond, because that's upper class, you wouldn't call it a beer diamond.
A geologist might.
They had to sell them, so they made a market for it
Right,
based on the
right.
colors. But the brown diamonds here are also, they're all colored by plastic deformation. So when these diamonds are deep in the earth, still very, very hot, instead of breaking, they're under sheer stress. But instead of breaking, they're kind of oozing a little bit, like the atoms sort of shift relative to each other. Sort of like toothpaste, you can think about it. And that, the features, they're actually clusters of what we call vacancies that form along those slips is what absorbs a lot of heat in the brown clay.
Thank
So
you.
You do see some of that here. You certainly see the brown diamonds are fairly common. And the clear diamonds quite often are similar to some other places in the world, but a much higher percentage of the clear diamonds are type 2A here for whatever reason. We haven't been seeing very many brown 2A diamonds here, which those tend to exist around the world as well. And then you have the yellow, which are colored by nitrogen, which is pretty standard. It's what we call aggregated nitrogen. So pairs or clusters of nitrogen atoms together, meaning that they've been in the earth for a while before they came out. And I think people estimated some of the diamonds here being a couple billion years old. So that would make sense. And only 60 or so million years ago that they came to the surface. So all that other time, right, they sat down there just kind of cooking, so to speak. But yeah, the 2As are remarkable because the work has suggested they form at 600 kilometers, whereas everything else is at 200 kilometers. And it's also thought that the lamproites and kimberlites in other places originate around 200. So it's a big story right now to try and figure out how we know these formed at 600 because there's minerals in there that don't exist, shallower. How they made their way up, and there's a few theories as to how maybe they came up in masses of rock that were less buoyant or whatever. But ultimately, they moved up and they got mixed in with the kimberlite. I always call the kimberlite school bus that picks kids up from different places, and so it kind of picked up the 2As and picked up the others. So it's unclear if something came all the way up or if something brought these up and then it all got sampled from the same place together. But either way, they got mixed at some point in time. And if you look at, I mean, I think he showed you the big 2A stone.
Yeah.
When you look at those, they look drastically different than the other diamonds that come out of here. And I can certainly envision the idea that they formed somewhere else.
Well, I always envisioned that when they all initially formed, they were like the classic octahedrons or cubes, but then during transport,
This diamond
they were
is this
ablated.
diamond.
Well, that's what's thought to have happened.
Or they were cleaved and then ablated, so you get a flat form like that.
The 2As, yeah, are thought to have undergone so much stress from coming deep in the earth, and they're also thought to grow rather big deep in the earth, and so they break up, and each piece then gets resorbed or dissolved a little
Right.
bit while it's still deep in the earth. You get all kinds of flat, irregular, weird shapes. All the other diamonds are resorbed, but they're resorbed from octahedra, so you can kind of envision an octahedron where the points go in, the edges dissolve in, and you get sort of these elongated, rounded shapes or these ball shapes.
That goes back to the crystallography of the diamond itself.
It does.
Especially with, when you have edges versus flats. Edges chemically etch.
And that's why they go in.
And so you wind up with a lot of rounded looking
Exactly.
stones. It's very similar. We stopped at a place where we had some gravel to look at today on the way down. And all that stuff started off as blocky. But during stream weather, stream tumbling and everything, all the edges wear
So you
away.
get nice round-
So you wind up with nice round pebbles and gravels. Yeah.
Yeah, I mean, it's very well known. I mean, in diamond, it happens because they're dissolving, because they're out of equilibrium with the rocks that they're in later. And, but yeah, that's the only explanation for type 2A diamonds all being irregular, is that they are deep, they break into smaller pieces, and then they resorb from those pieces. So they don't resemble the original crystal metal.
Yeah. And that's what killed this from being commercial. There was so much resorption, you probably lost 60% of the diamond value due to loss of size of these stones compared to where in the kimberlites pipes, they were pretty much at equilibrium, so you get nice clean octahedrons, which lend themselves to cutting rounds very nicely.
Certainly.
But you take these irregular shapes, it's, you know, the largest diamond that was ever found here, said, was Uncle Sam, and it was a little over 40 carats. And it had a major inclusion in it, so they had to cut that out. So you wound up with a stone that's about 20-something carats, a marquee-shaped stone. No, it wasn't marquee. They cut it as an emerald cut, and then later they recut it slightly to give it more brilliance
Oh, okay.
and eliminate a few of the smaller inclusions that were near the edges of the thing.
Yeah, I mean, certainly resorption to this degree does happen in other diamond deposits, but it's certainly pretty extreme here.
Yeah.
And you're right, it probably took larger
The
stones.
diamonds from India, as you well know, are almost all rounded. Even though they're found in street gravels, they were rounded in the original deposit.
Yeah, nobody
They
knows
weren't
where the original
rounded
deposits
by-
in India were. That's the wild thing. Most
Yeah.
famous diamonds in the world, and they don't, never seen the rock they came out of.
Right.
I mean, the rock, well, keep in mind, diamonds don't form in these rocks.
Right.
These are just transport
They're
rocks.
zinc crystals.
Yeah,
Born
exactly.
crystals.
Yeah.
Yeah.
One thing interesting to me as a diamond miner that you're always looking for a big diamond. The average diamond found here is a 20 point. And these four in particular are, or let's take these three larger ones. These are all huge. I mean, this is 10 times the average and, 20 times the average. And this type 2A diamonds must have been huge if they broke up and after resorption and after breaking, you end up with a 3.85 carat diamond. It started out really big.
Well, it's certainly, I mean, it's not proven, but it's widely thought because it's difficult to explain the irregular. And this is not just here, it's worldwide. These type 2A diamonds are always irregular and they're usually very resorbed. Even in places where you don't get a lot of resorption in the diamond, the type 2 diamonds that come from there are resorbed.
Are both of y'all chemists, geologists?
Geologists,
Geology.
Yeah, we both have PhDs in geology. So, yeah.
Would you show them how the FTIR machine works?
Sure.
Okay.
Yeah.
We'll take some diamonds and put on there.